All right, we'll go ahead and get started. This is the M-Cubed seminar, and I'm pleased to introduce Quinton Lawton. Quinton's interest in tropical meteorology originated from his upbringing in Houston, Texas, where he saw impacts of hurricanes on his local community firsthand. He went on to obtain a BS in meteorology from Texas A&M, and then a PhD in atmospheric sciences from the University of Miami in 2024, where he was advised by Dr. Sharon Majumdar. Quinton just recently started as an ASP postdoc fellow in M-Cubed, just a month ago or so, I think?
Like 2 months now,
okay.
Yeah.
His research focuses on the predictability and interactions of tropical waves, especially African easterly waves and equatorial waves. This research uses a combination of reanalysis, satellite, and numerical modeling systems. He also has experience with field observations, working as a mission scientist on the NASA CPEX-CV research campaign in 2022. Here at NCAR, he plans to investigate these research questions using MPAS-A. Welcome.
All right. Let me reset my timer here so I know what time I'm at. Let's see. All right, everyone. So my name's Quinton. Thank you for the introduction. You may have seen me walking around the halls over the last few months. So I'm here to talk to you about some of the work that I've done in the past, as far as my PhD, and also some of the work that I plan to do here at NCAR. Before I get into this, I just want to point out that research, as we all know, is this really collaborative endeavor. So I have a lot of other scientists and institutions to thank for helping me do all this work. I definitely didn't do all of this alone without the help of others. And I want to start out by kind of motivating this question by talking about waves in the tropics and the fact that weather in the tropics is generally dominated by tropical waves. So we'll focus on a few waves here of interest. I'm in particular interested in African easterly waves. These systems originate over the continent of Africa, and they can produce a lot of rainfall, and also equatorial waves, in particular things like Kelvin waves and equatorial Rossby waves. But as we know, our numerical modeling systems we have to understand how these waves interact with one another, not just how they behave on their own, especially in how this is represented in numerical models. And so, you may probably be familiar with these waves before, but just, a real high-level overview of these two kinds of waves. These African easterly waves are these synoptic scale, troughs that move off the coast of Africa and produce a lot of rainfall, especially in the Sahel of a region of Africa. They also can form into tropical cyclones, which is something I'll talk about today. And so you may have heard of this before. Often people are less familiar with these convectively coupled Kelvin waves. So these are equatorially trapped, eastward propagating tropical waves. And they have these these circulations in which we have an enhancement of convection in what we call the convectively active phase, and a suppression of convection in what we call the convectively suppressed phase. And we also have zonal wind and up and down circulations that arise from these Kelvin waves. And these are all based on this linear theory that was theorized many decades ago, but we know in the real atmosphere these waves look a bit different than in theory. And these Kelvin waves in particular are what we call convectively coupled, hence CCKW. And that means that this convection that occurs in the regions of this wave are intrinsically tied to their growth and their dynamics. So this convection can help slow down this wave and also is important for driving some of the dynamics. And the reason this is pretty important for us in the numerical simulation world is that we know that these numerical simulations tend to really struggle with these waves. And that's something I'll talk about in the latter part of this presentation. This is a pretty classic figure showing the progression of cloud features in a sort of idealized convectively coupled wave where we often have leading, shallow cumulus and then deep convection followed by stratiform convection. So this is something we see in the real atmosphere a lot. But these convectively coupled Kelvin waves, exist on these pretty large scales. But we know that in the real atmosphere, we have these scales of motion. So anywhere from synoptic scale down to the convective scale, the microscale. And so something that what I'm really interested in, is how all of these scales of motion interact with one another. In particular, you have things on these very large scales like Kelvin waves that can then, have linear and nonlinear impacts on things like African easterly waves and tropical cyclones. And all of this is connected in some way to convection. And so what I'll be talking about today is about some of these interactions, in particular about these Kelvin waves and these African easterly waves and tropical cyclogenesis. And so if you were curious, there has, prior to the work that I've done, there's actually been quite a bit of work on the relationship between easterly waves, Kelvin waves, and tropical cyclone formation. So we know that Kelvin waves in some previous studies have a statistical connection to the number of tropical cyclones. So this is a diagram from this Schreck 2015 paper, which illustrates the number of tropical cyclones lagged from the passage of a Kelvin wave on day 0. And so we see that in all basins, not just the North Atlantic, but around the world, we have genesis favored, or tropical cyclogenesis favored, in the 1 to 2 days following a Kelvin wave. And we also know from some previous work that Kelvin waves might modify convection over Africa, which could help trigger easterly waves. And in some recent work, we even know that Kelvin waves might be modifying the energy processes like barotropic energy convergence we know are important to African easterly waves. Now, there have been a lot of theories on why Kelvin waves are connected to tropical cyclogenesis. And prior to some of the work that we did, one of the more recent theories was this idea proposed by Carl Schreck in 2016, which I like to kind of think of this kinematic buildup process. So this is the idea that these Kelvin waves have these zonal wind anomalies. And so these zonal wind anomalies actually modify large-scale vorticity, or turning motions in the atmosphere. And so the idea that they proposed in their work was that these anomalous zones of vorticity can overlap that of disturbances moving the other way, like easterly waves. And that could help promote a deep vertically aligned vortex that could focus convective processes and encourage tropical cyclogenesis. And in particular, this is a schematic from that paper showing the zonal wind anomalies. We see that in the Kelvin wave, the zonal wind anomalies are actually tilted westward with height. And so the idea is that the low-level vorticity would build up, and a few days later, it would actually extend up into the mid-levels. And this is an interesting theory, but one thing that I had questions about doing my PhD was connecting these impacts to actually looking at easterly waves themselves. So these African easterly waves, we know they're important for tropical cyclogenesis, but they're also important for in situ impacts over Africa, and so they have impacts of their own beyond just forming tropical cyclones. And also, this theory and theories before really don't address directly the impacts that Kelvin waves are known to have on convection, moisture, and thermodynamics. And if this sounds familiar, Rosa Maria Sperius just gave a talk 2 weeks ago about this in aquaplanets, which I'll connect this to. This idea that trying to move beyond just the viewpoint of the dynamic impacts, but also thermodynamics and convection. So all of this background, I'm going to bring back to the 3 main things I want to talk about today. And these are 3 things I addressed during my PhD. The first is just building a climatology of how Kelvin waves impact easterly waves. And then trying to understand this in the context of convection and moisture, and in the context of these processes that we know are important to tropical cyclone formation. And both of these questions I addressed using primarily ERA 5 reanalysis data and satellite data. And then an interesting question beyond that is how we see these interactions in numerical modeling systems. And in particular, we focused on this idea of modifying Kelvin waves in simulations. And so that'll kind of compose of the third question. And then I'm going to talk about all of this at the very end in the context of my ideas and plans here at NCAR starting my postdoc. And so, again, the motivation here is that hopefully by addressing some of these questions, we can improve forecasts over Africa, over parts of the ocean, and then better understand this global system and the interactions across scales. And so I'm going to jump right into question number 1, which is the impacts of Kelvin waves on easterly waves. And this work, we do have 2 papers that address this, primarily one that we wrote in 2022. And before we really get into building a climatology, we have to actually identify these features in reanalysis data. So one thing I worked on a lot was building this African easterly wave tracker. So what we do is we actually identify easterly wave objects using this 700 hectopascal curvature vorticity field. And we use a very large database, so we have over 40 years. And this is just what the climatology looks like over our easterly wave data set. I just like to point out that we just recently turned this into a Python module. So anyone here who uses Python can do like pip install qtrack. Qtrack because I couldn't think of a name and my first name's Quinton. You can do pip install qtrack and actually do this yourself. So if you're interested in doing that, I'm happy to help set that up too. And then we also identify these Kelvin waves, and we're going to use a pretty standard filtering method where we use a frequency wave number filtering like the Wheeler and Colodis 1999 framework. And we're going to filter grid-sat brightness temperature. And this is just a schematic of the variance of the Kelvin band. So we're pulling out the Kelvin, the fields that are like Kelvin waves. And this is the variance of that band, showing kind of where Kelvin activity tends to be concentrated. And so we're focused here on the Atlantic, and while it's not as much as what we see in the Pacific, we do still see quite frequent Kelvin wave activity in the Atlantic. So what we're going to do is take our easterly waves that we identify and our Kelvin waves and build this climatology of what I call easterly wave Kelvin wave passages. So we're just looking at this box in the Atlantic and over Africa, and we're going to watch these African easterly waves, and they're going to move past our Kelvin waves. Kelvin waves tend to be constrained near the equator, or easterly waves are a bit further north. And then we identify when the easterly wave actually is aligned in longitude with either the convectively active or the convectively suppressed phase. And we use this to build composites of the African easterly waves fields. And the idea here is to understand what's happening in that vicinity of the African easterly wave when they pass Kelvin waves. And when we start out, we actually aren't even going to consider tropical cyclones. We're just going to really consider these African easterly waves themselves. And when you build this climatology, what's kind of interesting is that you actually find that these African easterly wave, Kelvin wave passages happen pretty frequently. It depends on how you define your Kelvin waves. So if you use a higher threshold, you get a lower percentage. But you see something between 40 to 70% of African easterly waves passing some sort of Kelvin wave in their lifetime. Again, depending on how you define it. And so what's kind of interesting when you think about this is we have the statistical connection of Kelvin waves to tropical cyclogenesis, but clearly this is happening all the time and we're not getting tropical cyclones. So it kind of points out that this mechanism is something that may not happen very often, but still could be important. So what are Kelvin waves doing to these African easterly waves? The first thing that we actually find out is that they modify the propagation speed of African easterly waves. So what we're looking at here is a composite over all of our sort of interactions. And our lines, the blue line is for the active part of the Kelvin wave being at day 0. The red line is the suppressed part of the Kelvin wave. And these are time lags. So this is the African easterly wave speed. On the right, it's negative. Sorry, these are backwards for some reason. So this is before and then after the Kelvin wave. And so we see this kind of reduction. Here's an arrow in case you can't see it. We see this reduction in the propagation speed of easterly waves following both the suppressed and active phase. It's kind of interesting that you see a similar response, but one thing to point out is that oftentimes your active phase is surrounded by suppressed phases. So we might be seeing a sort of lagged relationship where this reduction in speed for the active phase is actually following a suppressed phase before it. So I can't tell you exactly why this is the case, but there could be this sort of decoupling due to the reduction in convection. But this shows us that Kelvin waves are affecting the propagation of these easterly waves. They also seem to modify, at least temporarily, the fields around easterly waves in the vertical. So these are composites, and we're looking again at day 0 being the time of the active Kelvin wave. We're looking at averages surrounding the African easterly wave at various heights in the atmosphere, and anything not significant is hatched out. And again, the x-axis is flipped so that we can think of easterly waves moving right to left, kind of like they do in the atmosphere. And so what we see is this actual increase in the low level followed by the mid-level relative vorticity at surrounding these African easterly waves. And then you also see this anticyclonic anomaly aloft. And at the same time, we also see this modification to the specific humidity surrounding these easterly waves. And so this pattern actually on the left is very similar to what Carl Schreck proposed, which is the idea that these zonal wind anomalies from the Kelvin wave are superimposing themselves on top of the easterly waves. So we're seeing really a superpositional impact here. But this result on the right is actually something that hadn't been shown directly before, which is the idea that the field, the moisture around Kelvin waves are actually modifying the moisture around easterly waves. And this probably goes without saying when you think about convectively coupled Kelvin waves, but these Kelvin waves also impact the convective fields around easterly waves, such as their divergence profile and the diabatic heating. This is derived from ERA 5. And if you look at satellite data, which I don't show here, you also see these significant changes. So Kelvin waves are temporarily increasing the convection around easterly waves when they pass easterly waves. And just to kind of connect this a little bit back to start thinking about tropical cyclogenesis, we can build our own composites of the lag time between one of these Kelvin wave passages in the red versus the number of tropical cyclones. And we also find using our data set, which is just African easterly waves that develop into tropical cyclones, a significant increase in genesis following an active phase of a Kelvin wave. And we also directly show there's a significant decrease in the number of genesis events following the suppressed phase. And if you were here 2 weeks ago, and I'm just going to keep calling out Rosie's talk, this is actually pretty similar to what Rosie found in her recent aquaplanet simulation. So this is showing that sort of day lag in her paper, and we see this significant increase 2 days after the Kelvin wave. And the reason I'm pointing this out is that this gives me a lot of confidence that this is not just an artifact of what we're seeing in observations, but this also potentially is something we're seeing in a more idealized framework. And so just to kind of bring us back to this section's conclusions, what I showed was that we can build this climatology of these wave interactions and see that they happen pretty frequently, and that Kelvin waves can temporarily modify a lot of attributes of easterly waves. I showed you some of these, but also they modify things like vertical wind shear. And I didn't show you this, but it's something we talk about in the paper. When your African easterly wave is more equatorward or closer to the Kelvin wave, you see these impacts be magnified because the envelope of zonal wind and the convection of the Kelvin wave are overlap that of the easterly wave a bit more. So this is all interesting and fun, but one thing I was really curious about was actually connecting this to tropical cyclogenesis processes. So there'd been a lot of work before this that had been focused on just the basin-wide changes, but I was curious about thinking about tropical cyclones and how they form and trying to connect some of these changes to those processes. And to do this, we actually have to take a step back from Kelvin waves. So everything I just said about Kelvin waves, just completely forget it for a few minutes. And we're just going to talk about tropical cyclogenesis. And so what I'm going to show you right here is using our database of African easterly waves, we can build these composites of tropical cyclogenesis from African easterly waves. So this is a composite where on the x-axis we have a day lag. Now it's going positive because I like to make things confusing. And on the right side here we have tropical cyclogenesis. So this at the right-hand side is when genesis happens. And what we see is that in the 2 days prior to tropical cyclogenesis, here's big circles in case you can't see it, we have an increase in the diabatic heating, an increase in the convective coverage, and also an increase in the specific humidity around these African easterly waves. And this may connect back to this idea of environmental preconditioning. And this is the idea that to get tropical cyclogenesis, you actually have to precondition the atmosphere to be more moist and to support convection prior to genesis proceeding. And this has been shown in some idealized studies, but also similar observations to this, which we use ERA 5, have been shown using precipitation and using different frameworks. But the takeaway here for our purposes is that genesis is a multi-day process, and we really do care about the diabatic heating and the convection prior to genesis. Another process that we're going to talk about is something called convective aggregation. Convective aggregation is just the aggregation of convection into more concentrated, intense regions. And so often we think about this in terms of the vertically integrated moist stack energy. The reason we use this quantity is because it's generally conserved during moist adiabatic processes. And so it's often used as a proxy for convection. And so if you draw a box like we draw right here, if you have a lot of scattered, weak convection, you'll have a lot of these, like little, circles like this. But if that aggregates into a concentrated area, you're going to have this really concentrated, intense region, and the variance of moist stack energy in that box is going to go up. And so this is often what we think about happening in tropical cyclogenesis. You get convection that organizes and becomes very intense. And so I promise this is the only equation I'll flash up on the screen today. Can I promise that? Maybe. But what we can do is we can build what Alison Wing and Carrie Manuel did many years ago is come up with this clever equation to actually quantify the convective aggregation process. So if your moist stack energy in the H prime, the change in the variance of that moist stack energy, if that's positive, we can think of that as being positive aggregation. And that's driven by a few different processes. For example, we have the surface to the atmosphere enthalpy feedback. So often people will maybe call this the wishy term, if you're familiar with that. This is the idea of you basically input this enthalpy flux from the ocean to the atmosphere where there's already a lot of moist stack energy. And so you can think about this as being a feedback when you think about the fact that this enthalpy flux is primarily driven by wind speed. So as your wind speed increases, you're going to get more enthalpy flux where you already have a lot of convection. That's going to drive the circulation and cause more of this to happen. So it's a feedback. Another process that we talk about is this long wave radiational feedback. This is when you put more clouds where there are already clouds, in very simple terms. Some people call this a cloud greenhouse effect. The idea is that these clouds in the atmosphere, they relatively trap our outgoing long wave radiation. And so there's anomalous warming where we have a lot of clouds, and that drives this overturning circulation. And so that also can be this feedback process. And both of these things actually contribute to aggregating convection. And we also have some other terms that I'm not going to focus on in this talk that are generally seen as being less important for this particular problem. And so going back to our tropical cyclogenesis framework, we can look at the genesis again being composited on the right axis here. And we can look at our long wave radiational feedback term in the red and our surface enthalpy feedbacks in blue. And we see that in the days prior to tropical cyclogenesis, up to 2.5 days prior, you see this increase in the long wave radiational feedbacks. And this has been shown in many other ways in many other papers, but we see this in our climatology of easterly waves as well. And so the takeaway here is that this long wave feedback is an important process, and it helps speed up these surface enthalpy feedbacks that eventually dominate later in the life cycle of these storms. And so I went on a little detour here, but I'm going to bring us back to tropical cyclogenesis. And so remembering this figure, back to Kelvin waves, back to tropical cyclones, we had this statistical relationship between genesis in this time period where easterly waves that form in this time period that tends to be connected to Kelvin waves. So what we can do is we can actually make composites of just these tropical cyclogenesis events, just those that happen in this time frame after a Kelvin wave, and try to understand what impact the Kelvin wave is having on these genesis processes. And so this kind of gets summarized in this figure. So what we're doing in this figure is we're compositing all of these genesis cases. And I believe we have, something like 33 in here. And what we're doing is we're actually compositing around the day zero being the passage of a convectively active Kelvin wave. So this is diabatic heating. This is specific humidity. You actually see that at the time of the Kelvin wave passage, we have this initial increase in the diabatic heating and the specific humidity around African easterly waves. What's really interesting is that if you actually filter this and you separate this out into eastward and westward propagating components, where the eastward propagating component is probably connected to the Kelvin wave, you see that most of the signal actually seems to come from the Kelvin wave. So in other words, the Kelvin wave might be helping to jumpstart some of these preconditioning processes. And this may make sense when we look at the lag time that we see in observations in aquaplanets between the Kelvin wave and genesis. So it's about a 2 to 3 day process when you start this convective heating and this humidity and when you get genesis. So if the Kelvin wave is jump-starting this process, you would expect genesis to happen about 2 days later. And that's what we see in the statistical relationship between these two fields. Now we were also kind of interested in identifying why a lot of these Kelvin wave and easterly wave interactions simply don't result in genesis, because that actually happens quite a bit. And I have one bullet point that does a lot of heavy lifting, but what we did is we actually, in the paper, used a logistic regression to just pull out those African easterly waves that were statistically favorable to undergo genesis. And we compared those waves that pass Kelvin waves and resulted in genesis versus those that pass Kelvin waves and don't result in genesis, to try to understand what were the differences in the behavior between those cases with those different outcomes. And we did this for a lot of fields, a lot of characteristics, and we had practically no statistical differences between them except for the convective activity. So if you look here on the very right, this is a composite, and we're subtracting those non-developing cases from those developing cases, and we're compositing around the Kelvin wave. And we see those developing cases actually have more convective activity around the easterly wave than those that don't. So this is implying that the Kelvin wave might be eliciting more of a convective response around the easterly wave, thus driving genesis. And we see we don't have significant differences in things even like specific humidity. Now you may see a little error or a little caveat here, which is that, well, of course, developing waves are going to have more convective activity prior to genesis. And this is just the reality of using reanalysis data. It's really hard to separate out these processes and attribute them to the wave. Nevertheless, I think there is some, at least some implied evidence here that convection could be important for discriminating between the interactions that result in genesis. And we can also look at a similar framework and connect it back to convective aggregation. And we look at these long-wave radiational feedbacks, and we're looking again at the favorable developers versus the favorable non-developers. And we see that after the Kelvin wave, which is here at day 0, we see an increase in this long-wave radiational feedback in the day or so following the Kelvin wave. And so this is implying, again, we can't prove because we're using reanalysis data here, but this is implying that some of the changes the Kelvin wave is imparting to the easterly wave may be resulting in an increase in this long wave feedback. And we don't see the same difference when we look at the surface enthalpy flux terms. And again, sorry, Rosie, I'm going to keep connecting this back to your work because in the recent aquaplanets, we also find, we're showing here that the moisture and non-dynamical features are important. And this is also what they found in this recent publication on aquaplanets, that they found that the entropy deficit around easterly waves seemed to drive the differences in the ventilation index, which is implying, again, that moisture and thermodynamics are important for the impact of Kelvin waves on tropical cyclones. So I see this as being additional evidence that we should be looking beyond just this dynamic spin-up, but thinking about convection, thinking about moisture. So let's wrap this all back up into a section 2 takeaways. I love my little overview slides. And so I want you to take away here that we using this easterly wave climatology, we showed that this preconditioning and long wave feedbacks might be important to genesis, as other studies have shown, and that we theorized that Kelvin waves could encourage these processes through their direct modification of convection and moisture around African easterly waves. And we also identified that the main difference in these interactions that result in genesis is the easterly wave's convective response at the time of Kelvin wave passage. And so this could be something that might be useful for forecasting. If you see your easterly wave just blowing up in convection when the Kelvin wave is passing, it could indicate that it's more likely to result in genesis. And so all of this is really great, looking at reanalysis data, looking at satellite data, but there's just a lot of limitations to these data sets, one being proving cause and effect. And so this is what really drove us to look in a different direction, trying to understand how these Kelvin waves look and behave in numerical simulations. And I'm going to connect this back to what I just talked about by pointing out 3 of the main points and the caveats to them. So like I said, Kelvin waves modify convection and moisture around easterly waves, and they're statistically connected to tropical cyclogenesis. And we think the reason that's the case might be due to their impacts on processes we know are important to genesis. But there are two caveats to this. The first one is the big one, which is how do we directly attribute those changes in the outcome of genesis to the Kelvin wave? How are we sure that wave was just going to develop into a tropical cyclone on its own? And that's something that's really hard to prove using historical data. And then all of this actually there's this underlying motivation under all of this that by identifying these interactions, we can actually improve forecast. But this is assuming that our numerical models actually represent things like Kelvin waves and easterly waves. And so another caveat is understanding how these models represent these interactions. And often we think about these Kelvin waves as being these big, large planetary scale features that might be easy for a model to pick up. And the reality is that we still have a long way to go in terms of operational forecast skill of convectively coupled Kelvin waves. So there have been a lot of studies on this in recent years showing that Kelvin waves, we have very limited predictability of Kelvin waves in our operational models. This is just a study from a few years ago showing this is the skill correlation of the Kelvin waves precipitation this is the GFS models, the two versions of it. And we see that after even a few days, that skill drops off dramatically. And there's been a lot of speculation that this has to do with the coupling between convection and the Kelvin wave, and in particular, the representation of convection. And so this is something that, again, motivates us to look at these waves more closely in models. And so what I'm going to try to do, or what I tried to do for the last the last chapter of my PhD, was to modify Kelvin waves in these MPAS simulations. So if you're not familiar with a model for prediction across scales, it's a model being developed here at NCAR. And one of the reasons that MPAS is something we wanted to use is that at least in aquaplanet simulations and some limited case simulations, it's been historically very good at simulating Kelvin waves. So this is a figure that shows from this paper a few years ago from Falco and Rosie showing the contribution of, or the variance of different precipitation fields in different resolutions of MPAS models versus observations. And one thing you see here is that even at non-convective permitting scales, the Kelvin wave band seems to be, somewhat, similar to observations, implying that it's still able to capture Kelvin waves pretty well. And so maybe this is a little foreshadowing for our results here, but we'll get to that in a sec. And so the idea here is that we're actually, we developed this kind of amplitude modification framework and parameterized numerical simulations. So the idea here, it's not very complicated. We just changed the Kelvin wave at initialization. So we want to take our original Kelvin wave that in the vertical looks something like this, and we want to either amplify it or we want to dampen it. And so the goals for doing this is to illustrate how this could, what this may tell us about the dynamics of these waves, their impacts, and also whether it can change the outcome of, a poorly forecasted event. And so what we did for this paper was test this methodology on a particular historical case. And we chose this particular case. This is a case that, starts in September 24th of 2021. Exactly
what you did to sorry.
Yeah.
Could you say a little bit more about how you modified the amplitude?
Yeah, I have a slide coming up on that. So yeah, but if I don't answer your question there, I can go into more detail. Yeah, somehow this is a little out of order. I just want to highlight here that the case we chose was a case at which we had multiple Kelvin waves existing around the globe, including one Kelvin wave here in the Atlantic, which I conveniently circle with a big black circle, that was what I like to call high impact. So it was over 3 standard deviations from our climatology for the Kelvin wave, and it seemed to result in the formation or impacted the formation of a tropical cyclone. And so I kind of thought, well, perfect, we have this really strong Kelvin wave. It should be really easy to simulate this and to modify it and see what happens when we make it weaker or stronger. And we also had this other really strong wave in the Indian Ocean as well as 2 other strong Kelvin waves. And so to get more into the details of how we actually modify it, So we're going to build these, we're going to have these 8-day simulations. So we're going to have a set of controls. We have a 15 3-kilometer control. So these are run with the scale-aware Tikta scheme. And so this is a 3-kilometer inner mesh and a 15-kilometer outer mesh, centered on the Atlantic where that Kelvin wave, easterly wave interaction happened, because our original intention was to get at that question. But as you see, outcomes were a bit different. And then what we're going to do is we're going to simulate a set of these 30-kilometer simulations, and we also did a 15 3-kilometer one where we amplify the Kelvin wave in initial conditions. We either amplify the dynamic fields or the dynamic fields plus thermodynamics and moisture, and we do the same thing but by dampening it. And so let me show you how we actually do this. So how we modify this is we filter this IFS analysis data in the time period surrounding the initialization of our model, and we just pull out, using this FFT Wheeler and Colodis method, the Kelvin wave signal in various fields that we're interested in. And so, for example, we looked at U, V, temperature, and relative humidity at all model levels. Then we take this data and we're going to limit it to just the 20 south to 20 north region, because if you do this filter in the mid-latitudes, it pulls out things that aren't Kelvin waves. And then we're going to use this, and we're just going to use this filter data to either add or subtract from the initial conditions that we run our models off of. And so then what you do is you, for example, can multiply it by 2, and you can run a model which the initial Kelvin wave fields are a bit stronger. And surprisingly, this all balances out, and you end up getting a stronger Kelvin wave. And so just to, again, point out kind of the process here, we have these two controls, and we have a high-resolution amplified case, and then we have 30-kilometer cases where we either modify the U and V or the UV, T, and relative humidity. And so the question that comes out of this is that do modifications persist throughout the simulation length? And I'm not going to actually show, so when we published this, we did the 30-kilometer ones first, and then I did some work on this higher res one, which is in my thesis, but I'm not going to show you the results from this because it's effectively the same as the 30-kilometer results. Okay, so the question you probably have is like, okay, well, you just changed initialization fields. Does this actually change the Kelvin wave, the propagating Kelvin wave? And the answer is actually it does change the propagating Kelvin wave. So this is looking 4 days into these 8-day simulations. And what we're looking at in these fields, the shading is the filtered rain rate, so the Kelvin wave associated rainfall. And the contours are our upper level filtered U, zonal wind. So this is giving us an indication of somewhat the dynamics and the contours of the wave, and then the convection associated with the wave. I'm going to have more quantitative figures, but just from a quick glance, you see that you have more contours in the amplified case versus the control in the dampened cases. But something that probably stands out to you is that we have this really pronounced Kelvin wave-like signal in rainfall in the Indian Ocean, but we don't have much of a signal at all in the Atlantic Ocean, which was that very strong Kelvin wave that we were trying to simulate. And we can actually quantify this a bit more. So what we're going to do is look at all of our simulations and track the Kelvin wave and look at the rain rates and look at the rain rates for them. So this top figure is looking just at the Atlantic Kelvin wave, and this is following the Kelvin wave through its life cycle. The red colors, these are our amplified cases. The green and yellow are our dampened cases, the controls in blue. And what should have happened for my merge is in black. So the Atlantic Kelvin wave, there was not much of a convective signal in any of our models, even when we had the convective permitting simulation running. So even the convective permitting simulation, it does maybe capture a bit more of that filtered fields, but not even close to what we expect from observations. In contrast, our coarse 30-kilometer simulations, as well as our 15-kilometer outer mesh, seem to, they don't fully capture the Indian Ocean Kelvin wave, but they certainly show us a lot more of the characteristics of a propagating coupled Kelvin wave than our Atlantic wave. Another thing that pops out from this is if you look in the Indian Ocean wave, you see that our red versus our green and yellows, our amplified cases end up reaching a peak magnitude that's higher than that of the control and that of the dampened simulations. And so all of this is telling you is that this Kelvin wave is slightly stronger when you amplify it. And in fact, it seems to be, you seem to be able to modify it more if you modify not just the winds, but also the rain rates. Or sorry, also the thermodynamics and the relative humidity.
Could you remind me?
Yep.
Like if you plot, you've amplified things, right?
Yeah.
And you've also dampened them. Sorry.
Yeah.
So there's amplification and there's damping. In terms of these metrics, the amplification is how much?
I'm sorry, I didn't say that. So it's double the initial fields. So we take everything and the Kelvin wave filter signal is pulled out, and we just multiply it by 2 and put it back in. So
And half for the.
actually, no, we try to take the whole thing out. So it doesn't. So one thing that pops out of this is that you can try to remove the Kelvin wave signal, but in the models you'll still build up a Kelvin wave. So even though the outcome is dampening, but we try to eliminate it. And you also see in the upper level fields, so we're looking at the upper level velocity potential, which is kind of giving us an indication of the outflow at the top of the Kelvin wave. You see that in the Atlantic, you're actually able to, the amplification and dampening does seem to modify the dynamics, as well as in the Indian Ocean. But again, in the Atlantic, we don't see much of a convectively coupled Kelvin wave. So this is more akin to like a dry Kelvin wave. Another thing that kind of pops out here is that, like I said before, if you modify both the dynamics, just the wind, or you just modify the wind and you modify the thermodynamics, you see different responses. So we actually see evidence of this convective coupling because just by amplifying the wind, we actually change the rainfall. And if you amplify the wind and the thermodynamics, you get a stronger response in your dynamic fields. In other words, you see that the model is simulating that sort of coupling between convection and dynamics. But the thing that stands out here is what's happening in the Atlantic, and you'll be happy to know it was not just MPAS, but it was actually also the IFS model. So I worked a bit with the folks at UCNWF, and they looked at this particular Kelvin wave in their models, and they also found the contours in these diagrams is that Kelvin filtered field, and when they initialize at the same time as when we did the simulation, they don't get a Kelvin wave, but they do get one if they initialize it later. So this doesn't seem to necessarily be just an issue with the MPAS model, that there's something going on. And we also did modify the initial conditions in the Kelvin wave, like I talked about, and we didn't actually seem to change the outcome. So we're not quite sure what's going on basically with that lack of simulation. But we do see if we initialize these 30-kilometer runs later on in the period, we are able to better capture the Kelvin wave, just like we saw in IFS. So this is our control run, and then this is our filtered rain rate fields, and we initialize it at later dates, 2 days later on the very right. And so you see a much more pronounced Atlantic Kelvin wave when you initialize it later. Another thing, separate from this sort of modeling issue that kind of pops out of this, is that you can actually use this to understand a bit more about the Kelvin wave's dynamics. And so what you can do is you can actually build composites of your Kelvin wave over its lifetime and look at other fields we know are important to Kelvin waves, like the column saturation fraction and deep convective inhibition. So these are diagrams on the right showing the Indian Ocean Kelvin wave over its lifetime, composited in longitude. And you see different lines are different simulations. And without trying to make you squint here, what we see is that in our amplified cases, we actually have much stronger anomalies in deep convective inhibition and our column saturation fraction. And some previous work has indicated that deep convective inhibition helps control the precipitation onset in Kelvin waves, and that the column saturation fraction appears to set rainfall amounts. And so this aligns with this idea that in our simulations where we amplify it, we are actually producing these larger column saturation fraction anomalies that drives more rainfall versus when we dampen it. So returning to the takeaways from this section, so we can adjust Kelvin wave amplitudes by changing them at initial conditions, and we can use this to try to understand these waves. But we still clearly struggle with simulating some of these really strong Kelvin waves, even days prior to when they have pronounced impacts. And I think what this really drove home to me, and what I will connect to my work here at NCAR, is this idea that we need to understand the predictability of Kelvin waves before we try to understand how that impacts other processes. And so I'm just going to close in the last few minutes for questions with some of the outstanding questions I think this inspires and what I want to be doing here at NCAR to address this. And then we can return to the main conclusions and take questions. And so I see a lot of outstanding questions, but I think one of the biggest ones for me is when I was doing this modeling study, I had no real context for these really abrupt modeling failures of Kelvin waves. So I can't tell you if this is common, if it's more likely in the Atlantic, if it's because it's over land. And I think this really illustrates that we need to be doing some more work on the predictability or forecast bust of these individual Kelvin waves. And then we also want to understand, what factors might influence this. So, is it, the way our models represent convection? Is it something with land-based processes? And then once we can tackle these questions, we can hopefully use this sort of wave modification framework to better understand attribution. So if I change the Kelvin wave and make it stronger, does it lead to a tropical cyclone, or does it change the outcome? And ultimately, how does this all interact with features over Africa that we know are important? So like African easterly waves, of course, but also MCS systems, the West African monsoon. How does this impact predictability? And so just returning to this idea of this gap of not being able to simulate this Kelvin wave, I want to know, how common are these failures? Is there a regionality component? Are there downstream impacts? So one thing I've been starting to do here at NCAR is to actually go back into previous forecast systems and hopefully identify good and bad forecasts of Kelvin waves, which hopefully will motivate some modeling work into understanding, why these are different. Something I explored a bit in my thesis that didn't get published because we didn't have Atlantic Kelvin wave, in the convection, so how am I going to study it, is the attribution question for tropical cyclogenesis. If we change the Kelvin wave, does that change our outcomes? And finally, I think there's some ideas that we can learn from previous studies that have modified things like convection and moisture over regions like Africa, like some of the work that Kelly Nunez-Ocasio has done, and trying to understand, if we change moisture, if we change convective activity ahead of easterly waves or ahead of equatorial waves, does this impact their predictability? And so I'm going to stop there, take some questions, and I'll leave you on the main conclusion slide just to recenter back on what I talked about. So thank you for having me.
Time for questions?
Thank you. Really fascinating stuff. And I have a clarification question, though. Mm-hmm. You were talking about when the Kelvin waves interact the most with the easterly waves was when the crests were in a certain point in time relative to one another. And I just want to know exactly how crest was defined. I think I have a vague idea, but not a specific idea.
Yeah, my apologies for that. Yeah, so that's kind of, what I mean by crest is I just mean the center of the convectively active or the convectively expressed phase. That's what I meant by that. I say that because when you draw the signals relative to the easterly wave, they look like crests. So I guess in my head, I think crest, but yeah, it's the relative to the Kelvin waves convection modification.
On the subject of that interactions between the AEWs and the Kelvin waves, you mentioned this latitudinal kind of dependence of that, but what about a longitudinal one? Like, do you see different interactions over Africa versus Eastern Atlantic versus Western Atlantic? And I imagine that's important for the TC genesis, because probably most of it, I'm guessing, is happening in the Eastern Atlantic.
Yeah, that's a really good question, and there's some limitations with data sets here. So I had an African easterly wave tracker, and at the time of the study, it didn't really pick up a lot on the Caribbean easterly waves. So you have a low sample size. I did look at some of these differences. So there is, for example, a difference in the modification to wind shear that I don't really talk about here. So the Kelvin wave is going to impact the wind shear based on the background shear profile. So for example, when your shear profile is mostly easterly shear, what the Kelvin wave does to that shear is going to change versus the westerly shear. So we did show that in the paper. But in terms of actually looking at convection and moisture, when I tried to look at that, the sample size was just a bit too small to pull anything meaningful out of it. So I think it's a good space for like idealized or like other modeling simulations to fill that gap.
I think James. Oh, okay. James first.
Yeah, great talk. Thank you. I was interested in this preconditioning timescale before TC genesis, so and what sets it. So you talked about the role of Kelvin waves as in like providing a bump or to start the process. But is there a role of the Kelvin wave and maybe its propagation speed in setting that timescale of before genesis?
That is a good question. So that's not something I've really thought about with the timescale. One thing to keep in mind, we talk a lot about the statistical relationship being this time frame. But I'm not actually convinced that Kelvin waves are changing the ultimate outcome of an easterly wave. They may be just setting the time scale. So I think the way I think about this, maybe this is related to your question, is that when a Kelvin wave's active phase passes out of an easterly wave, it's like a window of opportunity. So it's providing that initial bump, or at least it's not providing a suppression impact. And that maybe sets a scale of when that storm might form. So but I haven't actually looked at like the propagation speed, maybe if you're propagating slower, there's a larger window. I think that's a good question that if we can get different speeds and like models, we might be able to tackle. Yeah, but that's good question.
I'm trying to think how to pose this. Like if you consider, say, a tropical cyclone, it's a coherent feature.
Mm-hmm.
There's a long history of people sort of removing or adding these things to simulations. And it works, not perfectly, but plausibly. Throughout the talk, you speak of Kelvin waves and African easterly waves as sort of things, right? Entities or features. But when you try and remove it from the simulation, it doesn't really respond like you've removed the feature, right?
Yeah.
So, do you have any thoughts about that? Like, I guess I feel like maybe Kelvin waves are not quite as precise or coherent as our language leads us to act like they are.
Yeah, no, I agree with you completely, and I think that's something I've thought about a lot. The reality is that the way we identify Kelvin waves, at least in this real data, is using either some sort of filtering method, some sort of projection method. There are ways to do it, different ways to do it, and they all have their downsides. And you're assuming something, so you're assuming that the signals in this spatio-temporal box is the Kelvin wave. But we know in reality that's not necessarily true. There's noise. So I think you make a really good point here that, for example, you can filter data and get signals that look like Kelvin waves that aren't at all Kelvin waves. They just happen to be propagating at the speed and on the scales that Kelvin waves exist in. And so, yeah, I think that's a big question. And I've thought about this a lot in terms of African easterly waves. African easterly waves, we think of these cohesive features. When you actually try to track them and measure them, you start questioning what is an African easterly wave. Because there's a point in time.
Your tracking is like a local tracking, right?
Yeah, so it's just a blob. I like calling it like a blob tracker. It's just a blob of curvature vorticity. I mean, you're just tracking that along. And the question is like, it may be a cohesive feature, but over time it may lose characteristics of African easterly waves. It may keep tracking it. It may lose an easterly wave that might technically be an easterly wave. So I think these are like important questions and like how we define features impacts, how we interpret them. So definitely, I think, thought-provoking and something I want to think about in the future, yeah.
Okay, question? We'll take a question from Slido from
Yeah.
Rich Rotino. What's the origin of Kelvin waves in general and in your study in particular?
Yeah, that's a good question. So in particular, I'm focused on the Atlantic Basin. So in the Atlantic Basin, there have been actual studies from a few years ago, a few studies that have shown that the origin of these Kelvin waves is roughly like 60 to 65% actually originate over South America. So that can be either due to, you can get like Rossby wave breaking, you can get in situ convection that's on the scale of Kelvin waves that drives these. And then the other 35% actually originates, over the Pacific or near regions where you have heating like the MJO. So often you get Kelvin waves propagating out from the MJO. And that's a good point, I think, to think about, our problem with modeling this Kelvin wave. The wave that we had problem simulating kind of amplified over South America. And so this may allude to the fact that something with South America could influence, for example, like land surface interactions may influence Kelvin wave growth. But yeah.
Okay. Let's go. Yeah.
Yeah.
But Rosie's simulations don't have Africa or South America, yet they have plenty of Kelvin waves. So any thoughts in the context of aquaplanet simulations?
Oh, geez. I haven't thought much about aquaplanets, but any simulation that you can get, heating on the scales of like a Kelvin wave can produce Kelvin waves. So in the MJO, for example, we get heating over the ocean that forms Kelvin waves on that scale. So but I don't want to speculate too much here. So.
Okay, another question from Slido. And then I think we'll wrap things up. We're getting on 3 o'clock. So Felco asks, how does the IFS handle Kelvin wave initialization compared to, say, mid-latitude troughs and ridges, given the scarcity of in situ wind observations?
Yeah, I don't know that question. That's the question I want to answer myself. I'm looking at some of these IFS simulations to look at origins of Kelvin waves. But yeah, I think that's a good point. Like, we don't have a lot of in situ observations, and so if they're over the ocean, we may not know what's going on. But yeah, that's a good point to follow up on.
Okay, let's thank the speaker once more.